Introduction: the breath of the world. Stand on a glacier at sunrise and you can hear it breathe. Not literally, of course, but the creak of ice, the drip of meltwater, the sigh of wind across snowfields all speak to a living system in motion. The glacier is growing or retreating, as it has for millennia. The air carries whispers of dust and salt from deserts and seas, thousands of kilometers away. The sun is warm, the wind is cold, and you are standing inside a story that began long before there were humans, and will continue long after we are gone. Earth has always been a restless, breathing planet. Its climate has swung between fire and ice, chaos and calm, shaping the evolution of life at every turn. Entire forests have risen and vanished. Oceans have swelled, shrunk, and traded places with deserts. Species have thrived under one climate and disappeared under the next. Climate is not just background scenery, it is the main stage on which the drama of life unfolds. But something is different now. For the first time in Earth's history, a single species has become powerful enough to tip the balance. We have cleared forests, moved mountains, lit up the night sky, and pulled ancient carbon from the ground to power our civilization. In just a few centuries, a blink in geological time, we have pushed the climate system out of its natural rhythm. The result is a planet that is heating faster than at any time in the last 55 million years. This is not just a story of catastrophe. It is a story of understanding. The more we study climate, the more we see how life and climate are partners in a great dance. Plants helped cool the planet 300 million years ago by burying carbon underground as coal. Microbes created the oxygen-rich atmosphere that made animal life possible. Today, we have the tools and knowledge to guide the climate, to slow the warming, restore ecosystems, and reimagine our role as caretakers of a living planet. This book is about that journey, past, present, and future. We will travel back through deep time to discover how Earth's climate has shifted over billions of years. We will see how climate shaped the rise and fall of civilizations, and how humans in turn began to shape the climate. We will explore the present moment, the challenges we face, the science that explains them, and the solutions that could lead us to a thriving, balanced future. Above all, this is a story about connection. Climate is not just physics and chemistry, it is forests, oceans, cities, economies, myths, and memories. It is as much about meaning as it is about measurements. By the end of this journey, you may never look at a cloud, a tree, or a warm breeze the same way again. Chapter 1: When the World Was Fire. The birth of a restless planet. Imagine standing on a world where the sky glows red with volcanic haze, where the ground trembles with constant eruptions, and where oceans, if they exist at all, are boiling cauldrons of steam. This was Earth in its first 100 million years, more alien than any science fiction planet. Earth was born from cosmic violence. Dust and rock clumped together under gravity, forming a molten sphere that was battered by asteroids and comets. One collision was so massive that it blasted off enough material to form the Moon, our planet's first and oldest companion. In this early period, the climate was chaos. Without a solid crust or stable atmosphere, heat radiated freely into space, then returned as solar flares and impacts reheated the surface. There was no weather yet, only storms of fire and stone. But slowly, over tens of millions of years, a balance began to emerge. The crust cooled. Water from comets and volcanic steam condensed to form the first global oceans. With oceans came clouds, rain, and the beginnings of the hydrological cycle, the first breath of the climate system we still live within today. Life enters the scene and changes everything. The first life forms were humble, single-celled microbes living near hydrothermal vents at the bottom of the sea. They had no lungs, no eyes, no sense of the sky above. But they were not powerless. Over time, some of these organisms discovered a way to capture sunlight and use it to make food. This process, photosynthesis, was revolutionary. It turned sunlight, water, and carbon dioxide into sugar, and released oxygen as waste. At first, this oxygen reacted with iron dissolved in seawater, forming vast deposits of rust-colored rock, the banded iron formations we find today. But as oxygen built up faster than the oceans could absorb it, it began to accumulate in the atmosphere. This was Earth's first great climate transformation. Oxygen cooled the planet by reacting with methane, a powerful greenhouse gas that had kept the young Earth warm. The result was what scientists call the Great Oxidation Event, roughly 2.4 billion years ago. Temperatures plummeted, glaciers spread, and Earth entered one of its first true ice ages. In other words, the planet's first climate engineers were microbes. Snowball Earth when ice ruled the world. Even after the Great Oxidation, Earth's climate continued to swing wildly. At least twice in its deep history, the planet seems to have frozen almost completely, with glaciers extending nearly to the equator. These snowball Earth events were global winters lasting millions of years. The world became so bright with ice that it reflected much of the sun's energy back into space, making it hard to escape the freeze. But volcanoes never stopped working. Over time, they pumped vast amounts of carbon dioxide into the atmosphere. With nowhere to go, since the oceans were sealed under ice, the greenhouse gases accumulated. Eventually, a tipping point was reached. The planet warmed rapidly, the ice melted, and Earth swung from frozen desert to steaming hothouse. Imagine living through that transition. Glaciers melting in torrents, seas rising hundreds of meters, continents greening in a geological blink. These extreme swings taught Earth a kind of rhythm. Over time, the carbon cycle, the constant exchange of carbon between the air, oceans, and rocks, began to stabilize. Mountains eroded, drawing carbon dioxide out of the sky and locking it in limestone. Volcanoes added carbon dioxide back, but at a slower, steadier pace. Earth had developed a planetary thermostat, not perfect, but good enough to keep liquid water and life going for billions of years. The Green Revolution, how plants cooled the world. Roughly 450 million years ago, another revolution occurred. Plants colonized land. Before this, continents were barren rock and sand. When the first moss-like plants began to spread across shorelines, they altered the planet's climate once again. Plants are master climate engineers. They pull carbon dioxide from the air, store it in their tissues, and eventually bury it when they die and are compressed into sediments. Over millions of years, this process led to a dramatic drop in carbon dioxide levels, so much so that Earth cooled enough to trigger new ice ages. The carbon that plants captured and buried during this era became coal, the very coal that humans would one day dig up and burn, unleashing that stored carbon back into the atmosphere. In a sense, the Industrial Revolution was powered by ancient sunlight, locked away by ancient forests. A planet in balance. By the end of this long chapter in Earth's history, a pattern had been established. Life and climate were partners. Life changed the air changed life. Feedback loops ruled the planet. A little warming could melt ice, which caused more warming. A little cooling could grow forests, which drew down carbon dioxide and caused more cooling. The system was self-correcting, but slow. When climate tipped too far, it took tens or hundreds of thousands of years to recover. What we call climate stability is really a fragile balance, maintained by oceans, rocks, plants, and atmospheric chemistry working together in a vast planetary dance. Why this matters today. This chapter of Earth's story reminds us that climate change is nothing new, but the speed and cause of today's change are unprecedented. Never before has one species, in such a short time, added so much carbon to the air. Never before has the thermostat been turned so quickly. When we look at today's rising carbon dioxide levels, we are not seeing something outside of nature's history. We are seeing nature's old mechanisms pushed to their limit. The planet will eventually find a new balance, but whether that balance will support the kind of civilization we have built is the question we must face. Earth has been through fire and ice before. The challenge and opportunity of our time is that we can understand what is happening and choose what comes next. Chapter 2: Icebound Earth and Fiery Warmings. The planet learns its rhythm. By about 3 million years ago, Earth had entered one of the most dynamic periods in its recent history, the Pleistocene. This was the age of ice, when vast glaciers advanced and retreated across the continents in cycles that lasted tens of thousands of years. At their peak, these glaciers were colossal, sheets of ice up to 3 kilometers thick covering North America, Europe, and Asia. But the ice ages were not permanent. Every so often, warmth would return, melting the ice and flooding coastlines, only for the cycle to begin again. These swings were not random. They were orchestrated by a subtle celestial rhythm, tiny variations in Earth's orbit and tilt that changed how sunlight was distributed across the planet. Milankovitch cycles, as scientists call them, are like the heartbeat of the climate system. When Earth tilts a little more toward the sun, summers become warmer, allowing ice to melt. When the orbit becomes more elliptical, the planet experiences more dramatic seasonal extremes. Together, these slow, predictable cycles created a climate metronome that has been ticking for millions of years. The sculpting power of ice. The glaciers of the Pleistocene were not just passive ice sheets, they were sculptors. As they advanced, they scraped valleys, carved fjords and ground mountains down to bedrock. They pushed rocks and soil ahead of them, creating the rolling hills and fertile plains that would one day support agriculture. When the ice melted, enormous floods roared across the landscape, carving canyons and reshaping rivers. The Great Lakes in North America are the scars left behind by retreating ice sheets, their basins gouged out by glaciers and later filled with meltwater. These dramatic transformations also changed the atmosphere. Cold, dry air favored open grasslands over forests. Dust storms spread minerals across continents and into the oceans, fertilizing plankton blooms that drew down carbon dioxide. The planet was a feedback machine, with ice, air and life working together to regulate temperature. The human dawn. It was against this backdrop of shifting climate that our ancestors emerged. The first members of the genus Homo appeared roughly 2.5 million years ago, right at the start of the Ice Age cycles. Climate instability may have been one of the forces that drove their evolution. In East Africa, where much of our early story unfolds, wet and dry periods alternated with unusual frequency. Forests would expand in wetter times, then contract into patches of woodland during drier spells, leaving open savanna between them. Our ancestors had to adapt, learning to walk long distances upright, to use tools and eventually to control fire. Fire itself became humanity's first climate technology. It provided warmth in glacial winters, protection from predators and a way to cook food, which gave our ancestors more energy from the same calories. Some anthropologists believe fire even extended our days, allowing us to gather at night and share stories, planting the seeds of culture. Climate as a shaper of migration. The waxing and waning of ice ages shaped not only the landscape, but also the paths humans took as they spread across the globe. During glacial periods, sea levels dropped by more than 100 meters, exposing land bridges that connected continents. The first humans to leave Africa may have walked across what is now the Red Sea floor, following coastlines into the Middle East and beyond. Later, as glaciers locked up vast amounts of water, the Bering Land Bridge connected Siberia and Alaska, allowing humans to enter the Americas. When the ice melted, these routes were drowned, isolating populations and shaping the diversity of human cultures we see today. The last glacial maximum. About 20,000 years ago, the last ice age reached its peak. Ice sheets stretched from the Arctic all the way to what is now New York City. Mammoths, woolly rhinos and saber-toothed cats roamed the tundra, while small groups of humans survived on ingenuity, fire and cooperation. Then a great warming began. By 12,000 years ago, the glaciers were in full retreat and sea levels rose at astonishing rates, in some cases by several meters per century. The climate stabilized just enough to create a relatively warm, wet period we call the Holocene. This new stability would change everything. The Holocene, climate's gift to civilization. The Holocene is sometimes called the long summer of human history. Its relatively steady climate allowed plants and animals to thrive, and allowed humans to invent agriculture. For the first time, we could settle in one place, store food and build villages. Climate was not perfectly static, of course. Periodic droughts and cold snaps still occurred, sometimes with dramatic consequences. The 4.2 kiloyear event, a severe drought around 2200 BCE, is thought to have contributed to the collapse of several ancient civilizations, including Egypt's Old Kingdom. But compared to the Ice Ages, the Holocene was a period of remarkable calm, and it was this calm that allowed cities, writing and complex societies to flourish. Lessons from the Ice Ages. The story of the Pleistocene and Holocene teaches us that climate is not just background scenery. It is a protagonist in the human story. Our bodies, our migrations, and even our cultures were shaped by glacial cycles and shifting rainfall. The fertile soils we farm today are gifts of the ice ages, ground and deposited by glaciers. The coastlines we know are the result of the last great melt. We are the children of ice and fire. To understand where we are headed, we must understand how the climate's natural rhythms created the stage on which we now stand. And it is on this stage that humanity has begun to alter the script, dramatically. Chapter 3: The Pulse of the Ice Ages. A planet with a beat. If you could watch Earth's climate over the past 3 million years as a time-lapse, it would look like the rise and fall of a slow, powerful tide. Temperatures would plunge as glaciers crept down from the poles, then surge upward as the ice retreated. Sea levels would drop hundreds of meters, then rise again, flooding coastal plains and reshaping continents. This rhythm is not random. It follows a pattern set by the geometry of Earth's orbit around the Sun. Serbian mathematician Milutin Milinković was the first to fully describe this orbital forcing in the early 20th century. He showed that 3 main cycles work together to set the timing of ice ages. Eccentricity. Earth's orbit shifts from more circular to more oval on a 100,000-year cycle, changing how far we are from the Sun during the year. Obliquity. The tilt of Earth's axis wobbles between about 22 degrees and 24.5 degrees over 41,000 years, affecting the intensity of the seasons. Precession. Earth slowly wobbles like a spinning top over 26,000 years, shifting the timing of the seasons relative to its orbit. When these cycles align to give cool summers in the northern hemisphere, glaciers grow and ice ages deepen. When they align for warmer summers, ice melts and the planet enters an interglacial, a warm period like the one we enjoy today. The ice ages, in other words, are not anomalies but part of a repeating planetary heartbeat. Humanity evolved, migrated, and began to invent culture to the rhythm of this climate drumbeat. The feedback loops that amplify change. While orbital cycles set the timing, they are too weak on their own to cause such massive swings in climate. The real power comes from feedback loops, amplifiers built into the Earth system. One of the most important is the ice albedo feedback. Ice and snow reflect sunlight, keeping the planet cool. When warming begins to melt ice, darker land and ocean absorb more heat, causing further warming and more melting. Another is the carbon feedback. Cold oceans absorb more CO2, cooling the planet further. As the planet warms, oceans release CO2, amplifying the warming. These feedbacks act like a lever. A small nudge from orbital changes leads to a big climate shift. The result is that the transition between glacial and interglacial states can be surprisingly abrupt. In some cases, temperatures in Greenland rose by 10 degrees Celsius, 18 degrees Fahrenheit, in just a few decades, faster than the lifetime of a single human. Abrupt shifts and the younger dryas. One of the most dramatic examples of sudden climate change occurred about 12,900 years ago. After thousands of years of warming and glacial retreat, the climate suddenly snapped back into near-glacial conditions, in what scientists call the younger dryas. The trigger was likely a massive outburst of freshwater from glacial lakes in North America, which flooded into the North Atlantic and disrupted the ocean circulation system that carries heat northward. With that heat conveyor belt shut down, temperatures plunged across the northern hemisphere for more than 1,000 years. For the hunter-gatherers of the time, this was a crisis. Herds of large game animals shifted or dwindled, plants became scarce, and survival grew more difficult. Yet it was during this period of hardship that humans may have begun experimenting with cultivating plants. In the Fertile Crescent of the Middle East, people began tending wild stands of wheat and barley, a practice that would soon transform into agriculture. When the younger dryas ended as abruptly as it began, the climate warmed rapidly. Within a few centuries, glaciers retreated, rainfall increased, and ecosystems stabilized. Agriculture took hold, villages grew, and humanity stepped onto a new path. The Holocene had begun, and with it came civilization. The gift and the trap of stability. The Holocene's relatively stable climate is sometimes taken for granted, but it was a rare gift in Earth's history. For more than 10,000 years, global temperatures stayed within a narrow range, allowing predictable growing seasons and the rise of cities. But this stability may also be a kind of trap. Civilizations became finely tuned to their climate, building infrastructure, farms and economies around expected patterns of rainfall, river flow and temperature. When climate shifts even slightly, through droughts, floods or temperature swings, these systems can be thrown into crisis. History is full of examples. The Akkadian Empire in Mesopotamia collapsed during a 300-year drought around 2200 BCE. The classic Maya cities were abandoned after a series of intense droughts in the 9th century CE. The Little Ice Age from the 14th to 19th centuries brought crop failures, famines and political unrest across Europe and Asia. These events remind us that climate change does not have to be as extreme as an ice age to profoundly shape human destiny. Preparing the ground for the Anthropocene. The story of the ice ages ends with a twist. As soon as the planet granted us a period of unusual stability, we began, slowly at first, to change the climate ourselves. Early farmers cleared forests to make fields, releasing carbon dioxide into the air. Rice cultivation in Asia produced methane, another greenhouse gas. Some scientists believe these early activities may have been enough to delay the onset of another ice age. If that is true, then humans have been climate shapers, not for 200 years, but for 8,000, gently nudging the planet's thermostat long before the Industrial Revolution. The next chapter of the story would see those nudges become shoves. Fire, steam, coal and oil would give humanity a new kind of power, one that could tip the balance of the planet's climate faster than anything in Earth's recent history. Chapter 4: The Agricultural Awakening. A turning point in human history. For nearly 2 million years, humans and their ancestors lived as hunter-gatherers, following herds, harvesting wild plants, and adapting to the rhythms of the seasons. Then, around 12,000 years ago, something remarkable happened. In several places around the world, different groups of humans independently discovered that they could shape the land rather than simply move across it. In the Fertile Crescent of the Middle East, they began to sow seeds from the wild wheat and barley they had long gathered. In China, they domesticated rice and millet. In Mesoamerica, they began to cultivate maize, beans and squash. In the Andes, they learned to grow potatoes and quinoa. This was not a single event but a slow revolution, the beginning of agriculture. And with agriculture came a new relationship between humans and the climate. Clearing the land, changing the air. To grow crops, humans cleared forests. At first, this was done with stone axes and fire, laboriously pushing back the wilderness to create fields. Every tree cut down or burned released carbon stored in wood into the atmosphere as CO2. Over generations, whole valleys were transformed from dense forest to patchwork farms. This process, repeated across the world over thousands of years, added up. By the time the first cities arose, enough forest had been cleared to measurably increase the concentration of carbon dioxide in the air. Rice farming in Asia brought another climate actor into play, methane. Paddy fields, which are flooded to keep weeds at bay, create perfect conditions for microbes that emit methane as they decompose organic matter underwater. Methane is a much more potent greenhouse gas than carbon dioxide, and over centuries, the spread of rice cultivation may have had a measurable effect on global temperatures. Some climate scientists, most notably William Ruddiman, have proposed the early anthropogenic hypothesis, the idea that these agricultural activities were enough to prevent the natural cooling trend that would have otherwise led to the next ice age. In other words, humans may have been tinkering with the planet's thermostat thousands of years before they knew what a thermostat was. Agriculture as a climate force. Agriculture did not just affect greenhouse gases. By replacing forests and grasslands with fields, humans changed the reflectivity, albedo, of the land surface, affecting how much sunlight was absorbed. Irrigation transformed deserts into green belts, altering regional humidity and rainfall. The very act of domesticating plants and animals created new ecological systems. Goats and sheep grazed hillsides down to stubble, leading to soil erosion. Large-scale plowing exposed soil to the wind, sending dust into the atmosphere and sometimes cooling the planet slightly. Humans, in short, had become a geological force, though still a small one compared to volcanoes and ice sheets. But the trend was clear: we were no longer simply shaped by climate, we were beginning to shape it in return. Climate collapse and resilience. Agriculture gave humans unprecedented control over food supply, but it also made societies more vulnerable to climate swings. Hunter-gatherers could move when resources failed. Farmers were tied to their land and to the weather. When rainfall patterns shifted or drought struck, crops failed and entire civilizations could collapse. The Akkadian Empire in Mesopotamia, one of the world's first great states, fell after a centuries-long drought around 2200 BCE. In the Indus Valley, a weakening of the monsoon may have contributed to the decline of Harappan civilization. The Mayan cities of Central America faced repeated droughts that likely pushed them past their carrying capacity. Each of these collapses was not just a tragedy, but a feedback event. When populations declined, forests often regrew on abandoned farmland, pulling carbon dioxide out of the air and causing small dips in global atmospheric carbon levels, dips that can still be seen in ice core records. The dawn of cities and industry. Despite these setbacks, the overall trajectory of human civilization was upward. By 5,000 years ago, city-states were rising along the Nile, the Tigris and Euphrates, and the Indus. Metallurgy, writing, and long-distance trade networks were emerging. Populations were growing, and with them, the demand for wood, grain, and pasture. This period marks the true beginning of humanity's transformation of the planet at scale. Entire forests were felled to build ships and temples. Vast irrigation works diverted rivers. Mining began to extract copper, tin, and later iron, leaving scars on the landscape and adding trace metals to the atmosphere, pollutants that would settle into distant ice sheets and be detected thousands of years later by scientists drilling for climate data. All of this was still small compared to what was to come. But the pattern had been set: more people, more land cleared, more energy consumed, more greenhouse gases in the air. A slow warming world. By the eve of the Industrial Revolution, around 1700 CE, atmospheric carbon dioxide levels were significantly higher than they would have been without human influence. The planet had been nudged toward warmth, not enough to cause alarm, but enough to create a slightly more stable, slightly more hospitable climate for agriculture. Then humanity discovered something that would change the game entirely: how to turn fossilized carbon, coal, oil, and gas into a near-limitless source of energy. The agricultural awakening was humanity's first act as a climate shaper. The Industrial Revolution would be its second, and far more dramatic act. Chapter 5: Coal, Steam, and the Carbon Explosion. The spark that lit the modern world. In the late 18th century, a quiet revolution began in the coalfields of Britain. For centuries, humans had relied on the same sources of energy: muscle power, wood, wind, and water. These were limited, local, and bound to the rhythms of nature. But beneath the hills of England and Wales lay a different kind of fuel: a dense black rock that contained the energy of ancient forests compressed over millions of years. Coal had been used in small amounts for centuries, to heat homes, smelt metals, and fire pottery. But as Britain's population grew and its forests were cut down, the demand for fuel rose. Coal became the obvious solution. Then came the invention that changed everything: the steam engine. Early versions were used to pump water from coal mines, but soon they were driving textile mills, powering locomotives, and propelling ships. For the first time, human societies had access to abundant, concentrated, and transportable energy. Energy that could do work on a scale previously unimaginable. This was the birth of the Industrial Revolution, and with it began humanity's first truly global-scale alteration of the climate system. The carbon tally. Burning coal releases carbon dioxide, just like burning wood, but the sheer scale of coal use was new. By the early 1800s, Britain's coal production had reached tens of millions of tons per year. The carbon that had been locked underground since the Carboniferous period was suddenly being released back into the atmosphere. This was not just a local phenomenon. As industrialization spread to Europe, the United States, and eventually across the globe, coal became the backbone of industry. By 1900, coal mining and combustion were releasing hundreds of millions of tons of carbon dioxide every year, a rate far beyond anything in natural geological history. And coal was just the beginning. The 19th century also saw the rise of oil, first as kerosene for lamps, then as fuel for the internal combustion engine. Natural gas followed, bringing cheap energy for heating and industry. Together, coal, oil and gas formed the trinity of fossil fuels that would power the modern world and load the atmosphere with greenhouse gases at an accelerating pace. Science begins to notice. Even as smokestacks blackened the skies over Manchester and Pittsburgh, a few scientists began to suspect that this new energy abundance might have planetary consequences. In 1824, French mathematician Joseph Fourier proposed that Earth's atmosphere acts like a blanket, trapping heat and keeping the planet warmer than it would otherwise be, the first description of what we now call the greenhouse effect. In the 1850s, Irish physicist John Tyndall demonstrated that certain gases, water vapor, carbon dioxide and methane, are particularly good at trapping heat. Then, in 1896, Swedish chemist Svante Arrhenius calculated that doubling carbon dioxide in the atmosphere would raise global temperatures by several degrees. At the time, this was seen as a curiosity, not a warning. Some even speculated that a warmer world might be more pleasant. Few could imagine the scale of industrialization that was coming, or how fast we would reach that doubling. The visible costs of progress. Industrialization transformed human life. Cities swelled with workers, railways stitched continents together, factories produced goods on a scale never seen before. But it also brought new problems that were impossible to ignore. Smoke and soot darkened the skies over London so much that street lamps burned at midday. Respiratory illnesses soared. Rivers became open sewers. In 1952, nearly 2 centuries after the Industrial Revolution began, the Great Smog of London killed an estimated 12,000 people in just a few days, a stark reminder that pollution could be deadly. But unlike smog or sewage, carbon dioxide was invisible, odorless and easy to overlook. It did not choke cities or poison rivers. Its effects were global, delayed and subtle, a slow turning of the planetary thermostat, rather than an immediate disaster. This invisibility made it a far more difficult challenge to recognize, let alone confront. The acceleration of the 20th century. By 1900, humanity was fully in the fossil fuel era. The 20th century saw energy consumption rise exponentially as electricity grids, automobiles, airplanes, and globalized industry spread. The First and Second World Wars spurred vast industrial mobilizations that consumed unprecedented amounts of coal and oil. The post-war boom of the 1950s and 1960s saw energy demand explode again as suburbs, highways, and mass consumer culture took shape. The carbon numbers are staggering. In 1850, atmospheric carbon dioxide concentration stood at roughly 285 parts per million, only slightly above pre-agricultural levels. By 1950, it had climbed to about 310 ppm. By the end of the century, it had surged past 360 ppm, and the curve was steepening. The Earth was entering uncharted territory, and for the first time, humanity had become the dominant driver of climate change, faster and more powerfully than orbital cycles or volcanic eruptions could ever achieve. The seeds of modern awareness. The mid-20th century was also when modern climate science truly took shape. Charles David Keeling began measuring atmospheric carbon dioxide at Mauna Loa Observatory in Hawaii in 1958, producing the famous Keeling curve. The line climbed steadily upward year after year, confirming that carbon dioxide from human activity was accumulating in the atmosphere. By the 1970s and 1980s, climate scientists were sounding increasingly urgent alarms. Computer models began predicting significant warming if emissions continued unchecked. Reports to governments warned of rising seas, shifting rainfall, and more extreme weather. Still, the Industrial Revolution had set humanity on a path that was difficult to slow. Fossil fuels had become the lifeblood of civilization. Entire economies, industries, and political systems depended on them. The challenge of cutting emissions would prove far more complex than discovering how to produce them in the first place. The planet enters a new era. By the dawn of the 21st century, the carbon explosion was undeniable. The Arctic ice was thinning, glaciers were retreating, and global average temperatures were climbing year after year. We were no longer just participants in Earth's climate system, we were the primary force steering it. Scientists began to argue that we had entered a new epoch, the Anthropocene, an age in which human activity is the dominant geological force. Future geologists, they suggested, might recognize the layer of plastic, concrete, and fossil fuel-derived carbon in the rock record as the marker of this new era. The question was no longer whether humans were changing the climate, but whether we could control the trajectory of that change before it destabilized the very civilization that fossil fuels had built. Chapter 6: Science, Politics, and the Birth of Climate Awareness. From curiosity to urgency. By the mid-20th century, scientists had more data than ever before. Charles David Keeling's meticulous measurements at Mauna Loa revealed a relentless rise in atmospheric CO2. The Keeling curve, now one of the most iconic graphs in science, showed two important things. 1. Seasonal breathing, a yearly sawtooth pattern as northern hemisphere forests absorbed carbon dioxide in spring and summer, then released it in autumn and winter. 2. Long-term growth, each year the baseline of carbon dioxide climbed higher than the year before. This was hard evidence that something fundamental was happening to the atmosphere, and that it was happening fast. By the 1970s, scientists were no longer asking whether human activities might be altering the climate, but how much, how soon, and with what consequences. The first climate models. Early computer models were crude by today's standards, but they told a consistent story. If carbon dioxide levels doubled, Earth's average temperature would rise by a few degrees Celsius. That might not sound like much, but scientists understood that even small shifts in global averages could profoundly disrupt rainfall, crop yields, and sea levels. These warnings were not limited to academia. In 1965, US President Lyndon B. Johnson's Science Advisory Committee released a report acknowledging that fossil fuel emissions could modify the heat balance of the atmosphere to such an extent that marked changes in climate could occur. This was one of the first times a head of state had been directly warned about climate change. Yet the report produced little action. Fossil fuels were driving economic growth, and growth was seen as an unquestioned good. A warming world becomes visible. Through the 1970s and 1980s, evidence mounted that climate change was not a distant possibility, it was already beginning. Average global temperatures were creeping upward. Sea ice in the Arctic was thinning. Glaciers from the Alps to the Andes were retreating. In 1988, NASA scientist James Hansen testified before the US Congress that the signal of global warming could now be detected in the data. The greenhouse effect has been detected, he said, and it is changing our climate now. Hansen's testimony electrified the media and brought climate change into public consciousness. Newspapers around the world ran headlines warning of a warming planet. Politicians began to speak of climate change as a serious policy issue for the first time. The birth of global cooperation. Recognizing that climate change was a global problem requiring a global solution, the United Nations established the Intergovernmental Panel on Climate Change, IPCC, in 1988. Its mission was to assess the scientific evidence and advise governments on policy options. The IPCC's first assessment report, published in 1990, concluded that human emissions of greenhouse gases were likely warming the planet and would continue to do so. This report set the stage for the Earth Summit in Rio de Janeiro in 1992, where the United Nations Framework Convention on Climate Change, UNFCCC, was signed. The UNFCCC was a milestone. For the first time, nearly every nation on Earth agreed to work together to prevent dangerous anthropogenic interference with the climate system. But the agreement contained no binding targets. It was more a statement of intent than a plan of action. Kyoto, and beyond. The first major attempt to set binding targets came with the Kyoto Protocol in 1997. Under Kyoto, industrialized nations agreed to reduce their greenhouse gas emissions by an average of about 5% below 1990 levels by the period 2008 to 2012. This was an important symbolic step, but it faced resistance from some of the world's largest emitters. The United States, then the largest carbon dioxide producer, signed the protocol but never ratified it, citing concerns that it would harm its economy and that developing nations like China and India were not subject to the same obligations. Still, Kyoto marked the beginning of serious international negotiations on climate, a process that would become more complex and urgent with each passing year as emissions continued to rise. The climate movement emerges. While diplomats debated, a grassroots climate movement was taking shape. Environmental organizations, scientists, and activists began to frame climate change as not just a scientific issue, but a moral one. Books like Our Common Future, 1987, popularized the idea of sustainable development. Documentaries such as An Inconvenient Truth, 2006, brought climate science to mass audiences. Activists staged demonstrations, called for divestment from fossil fuels, and pushed governments to act faster. At the same time, opposition to climate action grew. Some fossil fuel companies funded campaigns to cast doubt on the science, hiring lobbyists and think tanks to question whether warming was real or caused by humans. This manufactured uncertainty slowed public acceptance and delayed policy measures, years that might have been critical for mitigation. A world on the brink of change. By the early 21st century, climate change had become one of the defining challenges of our time. Extreme weather events, heat waves, floods, hurricanes, were increasingly linked to a warming climate. Coral reefs were bleaching. Permafrost was thawing, releasing methane. The data were now unequivocal. Atmospheric carbon dioxide had soared past 380 parts per million, far above any level seen in at least 800,000 years. Global average temperature was roughly 1 degree Celsius above pre-industrial levels, a number that might sound small but was enough to shift rainfall belts, intensify droughts, and melt ice sheets. It was clear that the era of discussion and debate was ending. The era of consequences had begun. A new phase of the story. The late 20th century and early 21st century were a turning point. For most of human history, we changed the climate unintentionally and incrementally. Now we understood what we were doing, and had to decide whether to change course. The next chapter of this story would be about solutions, renewable energy, carbon capture, new technologies, and the policies that could steer us toward a sustainable future. The question was no longer just scientific. It was deeply political, economic, and ethical. How do we balance the needs of a growing global population with the limits of the planet's atmosphere? Chapter 7: The Age of Solutions. A moment of reckoning. By the early 21st century, the evidence was overwhelming. The climate system was changing, and humanity was the cause. But a new question began to take center stage. Could we do something about it? For centuries, fossil fuels had been the engine of civilization. They powered industry, fed billions, and connected the world. The challenge was not simply technical but civilizational. How do we keep the benefits of modernity while reducing the harm it causes to the planet's atmosphere? This was not just a problem of restraint. It was a problem of imagination. The same ingenuity that unlocked coal and oil could be turned toward building a cleaner, more resilient world. The age of solutions had begun. The energy transformation. The heart of the climate challenge lies in energy. More than 3/4 of global greenhouse gas emissions come from burning fossil fuels. Solving climate change therefore means reimagining how we generate, store, and use energy. Renewable energy. Solar and wind power have become the flagship technologies of the energy transition. Once expensive and niche, they are now the cheapest form of new electricity in most of the world. Gigantic solar farms blanket deserts, offshore wind turbines spin steadily in the North Sea. Every year, costs fall and efficiency rises. Energy storage. Renewables are intermittent, but advances in battery technology are solving this challenge. Lithium-ion batteries, pioneered for laptops and phones, are now being deployed in grid-scale storage systems that smooth out fluctuations in wind and solar output. Research into alternatives, solid-state batteries, flow batteries, and even gravity storage, promises to make renewable energy reliable around the clock. Electrification of everything. Electric vehicles are replacing combustion engines. Electric heat pumps are taking over from gas furnaces. Even steel making and shipping, once considered hard to decarbonize, are experimenting with electric or hydrogen-based processes. The vision is clear: a world where nearly everything runs on clean electricity, and that electricity comes from the wind, the sun, and perhaps even the atom. Nuclear and next-generation power. Though controversial, nuclear power offers one of the few sources of carbon-free electricity that can run 24/7. Modern designs, smaller, safer reactors with passive cooling systems, aim to overcome the safety and waste challenges that have dogged the industry. Farther on the horizon lies nuclear fusion, the process that powers the sun. After decades of research, experimental fusion reactors are now producing more energy than ever, and private companies are racing to make fusion commercially viable within the coming decades. If successful, fusion could provide humanity with abundant, virtually limitless energy, a cornerstone of a stable climate future. Capturing carbon at the source. Even with a full-scale energy transition, some emissions will be hard to eliminate. That is where carbon capture comes in. Point source capture. Technologies can trap carbon dioxide directly from power plants or factories and store it underground in geological formations. Pilot projects around the world are demonstrating the feasibility of this approach. Direct air capture. More ambitious still are machines that pull carbon dioxide straight from the atmosphere, a kind of industrial-scale artificial tree. Though still expensive, costs are dropping, and some captured carbon dioxide is already being used to make synthetic fuels or concrete that locks carbon away permanently. Natural solutions. Perhaps the most elegant form of carbon capture is rewilding, restoring forests, wetlands, and grasslands that absorb carbon dioxide naturally while also supporting biodiversity and clean water. Regenerating the land. Agriculture, which once began the human story as a climate shaper, can now become a climate healer. Regenerative agriculture. Techniques like cover cropping, no-till farming, and rotational grazing can rebuild soil organic matter, turning farms into carbon sinks rather than carbon sources. Healthy soils not only store more carbon but also retain water, boost yields, and increase resilience to droughts. Precision agriculture. Drones, satellites, and AI allow farmers to apply fertilizer and water with pinpoint accuracy, reducing emissions from nitrous oxide and improving efficiency. Agroforestry and perennial crops. Integrating trees into farms and developing perennial grains can lock up carbon while providing food and habitat. This new agricultural revolution aims to feed a growing population while helping to stabilize the climate, a task as urgent as the first Neolithic revolution that gave birth to civilization. Geoengineering, a controversial safety net. If emissions cuts and carbon removal prove too slow, some scientists propose geoengineering, deliberate interventions in Earth's climate system to cool the planet. Options range from brightening clouds over the ocean to reflect more sunlight, to injecting aerosols into the stratosphere to mimic the cooling effect of volcanic eruptions. Geoengineering is controversial because of its risks, unintended consequences, uneven regional effects, and the potential to distract from reducing emissions. But it is increasingly being studied as a possible emergency measure, a fire extinguisher behind glass that we hope never to break, but might one day need. Building resilience. Even with aggressive action, some warming is inevitable. Sea levels will continue to rise for centuries, glaciers will keep melting, and extreme weather will grow more frequent. This makes adaptation as important as mitigation. Coastal protection, seawalls, mangrove restoration, and strategic retreat from flood-prone areas. Water management. reservoirs, desalination plants, and improved irrigation to deal with droughts. Urban design, heat-resistant cities with green roofs, reflective pavement, and expanded public transit. Disaster preparedness, early warning systems, and climate-resilient infrastructure to save lives when storms hit. Resilience is about more than survival. It is about building systems that can thrive under new climate conditions. A global effort. Perhaps the most important solution is cooperation. Climate change is the ultimate collective action problem. No single nation can solve it, but all can benefit from its solution. International agreements like the Paris Accord of 2015 have set targets to limit warming to well below 2 degrees Celsius, above pre-industrial levels, ideally 1.5 degrees Celsius. Meeting these targets will require massive investments, technology transfers, and unprecedented collaboration between governments, businesses, and citizens. Hope, agency, and the future. The solutions to climate change are not just technical, they are cultural and ethical. They require us to ask what kind of world we want to build, what we owe to future generations, and how we define progress. The same ingenuity that drove the Industrial Revolution can now drive a sustainability revolution. The same creativity that split the atom can be used to harness the sun. The same connectivity that built a global economy can mobilize a global climate movement. The age of solutions is not just about preventing disaster. It is about seizing an opportunity to build cleaner cities, healthier ecosystems, and a more just world. Climate change is not only a crisis, it is a chance to redefine our relationship with the planet that sustains us. Chapter 8: The Philosophy of Climate Stewardship. A new kind of power. Humanity is now the first species in Earth's 4.5 billion year history to understand the mechanics of its planet's climate, and to have the ability to change it at will. This is an astonishing fact. For most of Earth's history, climate shifts came from orbital wobbles, volcanic eruptions, asteroid strikes, or the slow drift of continents. Now, in the space of 2 centuries, one species has become as powerful a force as these ancient drivers. With that power comes responsibility. The question is no longer whether humans affect the climate, but whether we will guide that power with wisdom, or let it run unchecked. Myths of creation, myths of renewal. Ancient cultures saw the sky and the earth as living beings. In Greek mythology, Gaia was the primal earth goddess and Uranus the sky. Many indigenous traditions speak of a Mother Earth who nurtures and sustains life, and who must be treated with respect if balance is to be kept. These stories may seem like superstition to a modern scientific mind, but they carry a truth. They remind us that the Earth is not just a collection of resources to be exploited. It is a living system of which we are a part. Climate stewardship is not merely an engineering project, it is a moral one. It asks us to see ourselves not as conquerors of nature but as caretakers, participants in the great cycles of life, air and water. The ethics of the atmosphere. When we talk about the climate crisis, we often speak in numbers, parts per million, degrees Celsius, gigatons of carbon dioxide. But beneath the data lies an ethical dimension. Intergenerational justice. The decisions we make today will shape the lives of people not yet born. Do we have the right to leave them a hotter, less stable world? Global justice. Those who contributed least to the problem, small island nations, rural farmers, are often those who suffer first and worst. How do we share the burden of adaptation and mitigation fairly? Ecological justice. Do we have obligations to the other species with whom we share this planet? The coral reefs, the rainforests, the migratory birds? Climate stewardship demands that we expand our sense of responsibility beyond the present moment, beyond our own nations and beyond our own species. Learning from the keepers of the land. Around the world, indigenous peoples have long practiced forms of stewardship that keep ecosystems in balance. In Australia, Aboriginal fire stick farming maintained grasslands and prevented catastrophic wildfires for tens of thousands of years. In the Amazon, indigenous communities created rich, terra preta soils that supported agriculture without exhausting the forest. In North America, Bison herds were managed with fire and hunting practices that kept the plains healthy and productive. These examples remind us that living in balance with nature is not a utopian dream. It is a practiced skill, refined over generations. Modern climate solutions can draw wisdom from these traditions, blending ancient insight with new technology. Humanity as the planet's consciousness. Some philosophers have suggested that humans are the nervous system of the Earth, the part of the biosphere that can reflect, imagine, and plan. If this is true, then climate stewardship is a natural evolution of life's self-awareness. We are the first species capable of knowing the full story of Earth's climate history, the ice ages, the warm periods, the extinctions and recoveries. We are also the first capable of deciding what the next chapter will look like. In this light, climate action is not just about survival, it is about fulfilling a role. We are the storytellers of the planet, the part of nature that can look ahead and choose a future. A cultural shift. Solving climate change is not simply a technical challenge, but a cultural one. It requires a shift in how we measure success. For centuries, progress has been measured by growth, more production, more consumption, more extraction. But a climate-stable future may require us to measure progress by regeneration, more forest cover, more soil fertility, more biodiversity, more resilience. This does not mean returning to a pre-industrial world. It means building a new kind of civilization, one that thrives within planetary boundaries, one that sees the atmosphere not as a dump for waste gases but as a shared inheritance to be protected. A call to stewardship. We stand at a hinge point in history. Future generations will look back and ask what we did when we understood the stakes. Did we continue business as usual, or did we rise to the occasion? Stewardship does not have to mean sacrifice alone. It can mean cleaner cities, healthier food, restored landscapes, and a sense of belonging to something larger than ourselves. It can mean reimagining human purpose, not just as consumers and competitors, but as caretakers and collaborators in the grand experiment of life on Earth. The climate story is no longer just about the past. It is about the future we are writing, right now, in real time. Conclusion: shaping the next chapter. The story we have followed began in fire. 4.5 billion years ago, our planet was a world of molten rock and poisonous skies. It cooled, it rained, it breathed. Life arose in the oceans and reshaped the atmosphere, sculpting the world we know today. Ice came, ice went, and with each cycle the face of the Earth was remade. Then came us. For most of our history, we were small players in a vast drama, nomads moving with the seasons, surviving by reading the rhythms of sky and soil. Then, with agriculture, we began to leave our mark. With coal and oil, we became a planetary force. In just a few centuries, we have tipped the carbon cycle, warmed the air, melted glaciers, acidified oceans, and changed the chemistry of rain. We are no longer passengers on this planet. We are shapers of its destiny. This could be a cause for despair, but it need not be. Understanding the scale of our influence is not just a warning, it is an invitation. The invitation is to step into a new role, that of stewards, not just survivors. The climate crisis is at its heart a story of imbalance, of carbon out of place, of landscapes stripped bare, of species pushed past their limits. But imbalance is not the end of the story. The Earth has always been dynamic, always capable of renewal. The question is whether we will help or hinder that renewal. We have the tools. Solar panels now drink in the sun's power more efficiently than any leaf. Wind turbines capture invisible rivers of air. Carbon can be drawn down by forests, by soils, and even by machines. We know how to grow food without depleting the ground beneath it. We know how to build cities that are green, full, and resilient. But the deeper challenge is not technological, it is cultural. We must redefine what we mean by progress. For centuries, success was measured in how much we could take: more wood, more coal, more oil, more land. The future calls for a new metric: how much we can restore. How much carbon we can return to the ground. How many rivers we can clean. How many species we can bring back from the edge. This is no small task, but neither is it impossible. We have turned the tide before. We saved the ozone layer. We brought bald eagles back from extinction. We made rivers run clear again. Each time, it began with a recognition that something was broken, and a collective choice to fix it. What is unique about this moment is that the choice is planetary in scale. We are being asked not just to protect a forest or a species, but to balance the great breadth of the world. If we succeed, the payoff will be immense. A planet where the air is clean, where food is grown in harmony with the soil, where cities hum with renewable power, where coral reefs glow with life, where human society flourishes without overheating its only home. And perhaps most importantly, we will gain something harder to measure but deeply valuable, a renewed sense of belonging. We will know that we are not an alien force upon the earth but its consciousness, the part of it that can dream, decide and care. Future generations will look back at this century as a hinge point in history. They will either see it as the age when we burned too brightly and dimmed the future, or the age when we awakened, when we learned to balance, when we chose renewal over ruin. The earth will go on breathing, with or without us. The question is whether we will be part of its song.